Good afternoon, everyone. This is the third and final live session on the Chemical Reaction Engineering Course 1. And in this course, basically we have divided into two sections. One is reaction kinetics and the reactor design. In the last two live sessions, we have discussed about the reaction kinetics and most of the part of the reactor design, where we consider in the reaction kinetics part, we consider different kinds of mechanism, different kinds of reactions that may happen, and how to analyze the data experimentally, obtain data, how to find out the kinetics for a particular reactions, how to observe a particular mechanism or propose a particular mechanism and confirm it experimentally, that we have discussed in the first part. And in the later part, we have discussed the its design. Both three idealized reactor we discussed. One is basically batch reactor, which are commonly used for small scale manufacturing industries, but pharmaceutical industries. And if we need to large scale production, we need to consider the continuous reactors. And two idealized reactors which we have discussed, basically the plug flow reactor and the mixed flow reactor, or the MFR. We have discussed different other reactor kinds, reactor arrangements, and how to optimize the volume needed for the particular operations. And we have compared the performance equations or performance of each reactor, which one is better compared to the other one. If you have a choice of reactor, how you utilize them for basically for your production industries, and which reactor will come first and which will come later, that also you have done the optimizations of the reactor volume and the conversion. Although all these arrangements will finally be governed by the economics of the process that we have discussed. In the last part of this course, in the last 2 to 3 weeks, you have learned non-ideal reactors, but mostly homogeneous reactors, non-ideal homogeneous reactors. Heterogeneous reactions we generally considered in the next another course, which is reaction engineering 2. So in the non-ideal reactor, the residence time distribution is an important parameter which we need to concern, and residence time distribution actually tell us the degree of mixing in a particular reactor. As we have considered, if you consider batch reactor, that means you have a simple container and you have a starter connected with it. So the content of the reactor are continuously mixed or thoroughly mixed, they are homogeneous in nature. Similarly, if you considered a flow reactor like a mixed flow reactor, there also the content of the reactant and products, content of the reactor are thoroughly mixed. But in case of plug flow reactor, the mixing among the reactants are not there. There is no axial mixing in a particular tubular reactor, but there is homogeneous mixing along the radial directions of the plug flow reactor. And we can change this degree of mixing in a plug flow reactor if we have a recycled reactor. We can recycle some part of the product to the back to the reactor inlet, and which will mix with the fresh reactant. So you can change the recycle ratio, and you can change the degree of mixing. Okay, so from starting from plug flow to mixed flow, you can achieve any degree of mixing in the reactor. So, but the degree of mixing are bound by two idealized reactor. One is ideal plug flow reactor, where we consider there is no mixing in the axial directions or along the length of the reactor. But in case of CSTR, we consider complete mixing inside the reactor. So these two idealized reactors, the mixing is given by a bound, lower and upper bound. In one case there is no mixing, in other case there is complete mixing. Okay, but in reality the real reactors are actually neither unmixed nor completely mixed. So they are partially mixed in the real reactors. So that is why to characterize the reactor performance, we need to understand the degree of mixing. One of the measure of the degree of mixing is the residence time distribution. And you know how to measure the residence time distribution in a particular reactor. It is basically doing a tracer study, or radioactive tracer or color tracer you can incorporate at the inlet of the reactor, and you can measure the concentration of the tracer at the outlet, and you can see the how long each tracer stays inside the reactor. It is like a as if you are sitting outside or at the exit of the reactor, and you are asking each and every element which is coming out from the reactor, and you are asking, hey, what's your age? And then you can note down your age, and actually then you can compare how long each element stays inside the reactor and their age distributions. So if you know the idealized reactor residence time distribution of the idealized reactor, which we have discussed in the class, how it would look like for ideal plug flow reactor and ideal CSTR, how their residence time distribution curve look like. And residence time distribution is characterized with a dimensionless number. It's called the exit age distribution function, and that you know how to from experiment only you can measure concentration versus time, and from there you know how to calculate ET versus T curve, ET curve. Okay, exit age distribution curve, and you can plot it and see their distribution of the residence time. If you consider ideal plug flow reactor, there is no age distribution. Each element in a plug flow reactor remains same length of time inside the reactor. That is why they do not have a age distribution. So they have a constant age. So its exit age distribution function is a Dirac delta function having no infinite length with zero width, that you have learned in the course. In the later part, we try to use the residence time distribution function and we try to model the reactor. There are different type of model which we have discussed: 0 parameter model, 1 parameter model and 2 parameter model. So different parameter models we have discussed, and 3 important model which we have discussed in this course is segregation flow model, tank in series model and axial dispersion model. The concept of segregation flow model should be very clear to you, as already discussed in the lecture. The conversion, when you will calculate for using the segregation flow model, you need to consider the reactor content is not, all the element inside the reactor is not completely mixed with each other. Every element inside the reactor keep their identity separate among the other elements. So they are not mixed together. That is segregation among the elements of the fluid inside the reactor. But for each element, inside each element, they are completely mixed like a batch reactor. Okay, so when you calculate the conversion starting from their age distribution 0 to infinity, the in the integral sign you have to take the conversion of a batch reactor. Okay, conversion in a batch reactor, and then sum up all the conversion of their age starting from 0 to infinity. Okay, so each tiny element in a bigger mixed flow reactor, each tiny element inside the reactor is treated as a batch reactor. Okay, and each batch reactor conversion you can calculate, that you include over there sum of all the conversion, then you can calculate the mean conversion in the reactor. That is the concept of segregation flow models. Okay, and tank in series model, that also you have learned. Basically, if you take CSTR, say volume V, total volume is V of a particular CSTR, and you distribute this volume V to n number of small volume V1, V2 to Vn, small volume, and you connect them in series, and you calculate the conversion in a single reactor of volume V, and in a n number of reactor connected in series having the total volume V, which is equal to V1 plus V2 plus V3 to Vn. And you would see that the conversion are not same. So when this number of small volume of the reactor connected in series tends to infinite, the conversion will be equivalent to a plug flow reactor. That means the with infinite number of CSTR having the total volume to a single plug flow reactor will be same. That's what we have discussed in tank in series model. Okay, and another model which is the axial dispersion model. Axial dispersion means in ideal case the dispersion along the y-axis, along the radial direction of a tubular reactor is infinite, whereas along the axial direction the dispersion or diffusion of the components of the reactants are 0. Okay, is 0. So we need to see in the real reactor how much there is dispersion along the axial direction. To quantify that, we use one dimensionless parameter is known as the Peclet number. Okay, which quantify depending its low and high values. You can say that the if Peclet number of these, then it will be no highly dispersed and close to CSTR. If dispersion is very low, it will be close to ideal drug flow reactor. So axial dispersion models. So different parameter models we have discussed, and then we try to know model the different kind of reactors using this one parameter, two parameter, and three, one zero parameter, one parameter, and two parameter models. We could not consider a large number of variables to design the model, that means 3 parameter, 4 parameter and 5 parameter and so on. We cannot increase too much, because if you increase the variables or number of parameters to a higher number, you can know any system you take, it will feed the data. So that does not make the actual happenings in a real reactors. The models basically what we consider have a physical significance to represent the physical system in a mathematical form which closely resembles to the experimental data. Okay, so models should be not more than 2 parameters in case of any reactor design. Okay, so that's all overall what we have considered in this course, and I will be happy if you have any queries related to this course. Regarding the questions paper and in your exam, final exam, you know all those will be declared. It will be similar to MCQ and alphanumeric questions, as it is given similar pattern in your assignments. You had certain queries in the assignments. There are some typos or which our technical assistants, teaching assistants, they are actually looking after to correct those errors, and you don't have to worry about if there is any anomaly will be rectified, and you will be given the revised score in your assignments. And try to go through the lecture materials and try to understand the concept, try to solve more problems following Levin's field and Fogler's book. These are the two textbooks which we have considered, and I hope you will be perform well in this course. Thank you. Anyone is there? If you have any queries, please post your queries so that I can answer. So as I said, already said, one of you are asking regarding the final exam pattern. Basically, there will be MCQ type of questions along with numeric values. You have there fill in the blanks type questions. So you have to solve the problem and give the values. That may be decimal number or any numeric values. So that is the pattern. One thing I would like to remind you that uh, you see the autocatalytic reactors and autocatalytic reactions and its concentration profile for reactants and products. So you can see that the parabolic profile you will get for the product, and reactants will always will exponentially drop reactant concentration, and the maximum conversion of the reactants will occur at the 50% concentration of reactants as well as of the products. Another important thing to remember for the autocatalytic reactor is that you need to have certain products at the beginning to start the reaction. Autocatalytic reaction means the product is catalyzing the reaction. So to start the reactions, you need to have certain products. So if you use ideal CHTR, a plug flow reactor, in that case it would be difficult for the autocatalytic reaction to proceed. So any other queries? Please post your queries so that I can answer. Whenever you have any queries, you can just post in the discussion forum. I will be happy to reply your queries. Okay, so while learning during your exam also you might be facing some problem in your understanding or solving some problems. Try to post your queries in the discussion session. Okay, thank you very much. Since there are no queries, I think no, you will be able to understand most of the lectures which are discussed no, in the class, in the no, lectures which are given. And even then, if you have any queries, please post your queries in the discussion forum. I will be happy to answer. And good luck for your exam. Thank you very much.